So let me start by thanking the organizers for inviting me here. It's a wonderful conference, and we all should thank Victor for so much hard work he has done for this conference, and Pedro. Yeah. Okay. And this is joint work with my student Kriti Goyal and Vivek Mukundan, who was a student of Bernd Ulrich. He visited Bombay for a year and got me interested in characteristic P, which I avoided for 30 years. Yeah. In fact, the last course that I took from Craig was devoted to tight closure. And there was an exercise which was never published, and I want to show you the use of that exercise. It's in my lecture notes. So there are many things which we learn but we forget and come back again. Yeah. Okay, so the theme of this talk is to convey to you that coefficients of Hilbert-Samuel polynomial can detect properties of local rings. This is a running theme since 1960, ever since Theorem of Nagata came out. And properties like Cohen-Macaulay's regularity can be detected from the few coefficients of the Hilbert-Samuel polynomial. And that theme is also applicable for tight closure. And I want to show you that characteristic P singularities can also be detected by certain Hilbert-Samuel polynomial. Okay. All right, so let me recall. We have a local ring with residue field K and dimension D. And local ring will mean Noetherian local ring if I don't say this. Then the associated graded ring is polynomial ring in D variables. And therefore, we can calculate the Hilbert-Samuel function of the maximal ideal, that is n plus d minus 1 choose d for all n, and therefore the multiplicity is 1. And the converse is not true. If the multiplicity is 1, the ring need not be a regular local ring. This is the standard example. Take the local ring, power series ring in 3 variables, go mod the ideal xy, xz. This has 2 minimal primes of different dimension. So this is not what is called an unmixed local ring. A local ring is unmixed if its completion has the property that all associated primes have equal dimension. Okay. This is not unmixed, and that's what goes wrong. And Nagata proved. And this ring is not even Cohen-Macaulay because the zero ideal is not unmixed. So a Noetherian local ring is unmixed if every associated prime of the completion of R has the equal dimension, which is dimension of R. And Nagata proved that a local ring is regular if and only if R is unmixed and multiplicity of M is 1. Okay. Yeah. There are many proofs of this theorem. I will not go into this. This is proved in section 40.6 of Nagata. You can read. He makes use of many things: associativity formula, completion, creating an infinite residue field. So the standard tricks in Hilbert-Samuel function theory were already there in Nagata's book, and that's what we continue to use.
Which we cannot read because it's out of print.
Nagata's local ring is back in print. You can download PDF file from many sites.
Is it in print or somebody just copied it?
Yeah, somebody copied and put it online. It is not in print. Yeah, but you can find. I can share a copy with you. Yeah, right. Yeah. Okay, right. So, of course, once Nagata comes out with such a criterion, it's natural to ask whether we can find criteria for other properties of local rings like Cohen-Macaulay property or Gorenstein or complete intersection, and whether these properties are hidden in the coefficients of Hilbert-Samuel polynomial. This is indeed the case, and I want to show you 3 generalizations of Nagata's theorem. And so first one is by Northcott. Northcott's theorem about the first coefficient, not E0, but the next coefficient in the Hilbert-Samuel polynomial. So let me put up the notation. Take an M primary ideal of same local ring. The Hilbert function is length of R mod IN, HIN. And this is for large n given by a polynomial of degree d. D is the dimension, crude dimension of the local ring. And we write this polynomial in this fashion. So these coefficients E0, E1, ED. These are the Hilbert-Samuel coefficients. And this number E1, few years ago, Vasconcelos called it Chern number of an ideal. And I talked to Dale day before yesterday, and he tried to explain me why it is called Chern number of an ideal. The motivation comes from geometry. Yeah. So Northcott proved the following generalization, but it is in Cohen-Macaulay rings. Let R be a Cohen-Macaulay local ring, I an M primary ideal. Then E1 is 0 if and only if I is a complete intersection. So in regular local ring, if you look at the Hilbert-Samuel function of the Hilbert-Samuel polynomial of the maximal ideal, it has only top coefficient, and E1 is actually 0. But this proves the converse, that E1 of maximal ideal is 0, then maximal ideal is a complete intersection, and therefore the ring is a regular local ring. So in that sense, it can be considered as a generalization of Nagata's theorem for Cohen-Macaulay rings. Yeah. Then here is a generalization of Nagata's theorem by Huneke. Let me recall for you the definition of Serre's condition Sn. A finite module M over a Noetherian ring R satisfies Serre's condition Sn if for all prime ideals, the depth of M localized at P is at least the minimum of dimension of M localized at P and N. And Huneke proved the following result in '82. It's a 2-page paper in Proceedings of AMS, but beautiful proof. I ask you to read it in half an hour. And there is an open problem if you are interested in working. Take a local ring of dimension D with residue field K, and it should be complete and containing a field. Suppose R satisfies Serre's condition Sn and the multiplicity is at most n, then the ring is Cohen-Macaulay. Okay. This is indeed a generalization of Nagata's theorem. Let me show you how. So proof of Nagata's theorem. First of all, by standard tricks, we can assume that the residue field is infinite, and the condition, Serre's condition Sn and multiplicity is at most n, they pass to the completion, and the Cohen-Macaulay condition descends from the completion, and therefore we can complete the local ring. Okay. But here is a crucial assumption here: the ring contains a field. We can't do that. Yeah. Exactly. I'm going to state that.
So the Nagata's theorem, his full theorem, doesn't follow from it? Or?
Nagata's theorem doesn't follow. It follows only for rings containing fields.
Yes, okay.
Right. Yeah. Okay. So assume K is infinite and R is complete. Since R is unmixed, since it satisfies Sn, and for Nagata's theorem, the ring is unmixed, and therefore it satisfies S1, and the multiplicity is 1. And therefore, look at n equal to 1 case in Huneke's theorem, and that says that the ring is Cohen-Macaulay. Once you have the Cohen-Macaulay property, then we can pick a minimal reduction of maximal ideal so that length of R mod J is multiplicity of J, and multiplicity of J is multiplicity of M, because J is a reduction of M, and this is given to be 1 in Nagata's assumptions, and therefore length of R mod J is 1, and therefore J is the maximal ideal, and therefore the ring is regular local. So the real point is Cohen-Macaulay property through these assumptions. Once you have Cohen-Macaulay property, regularity follows easily. But the catch is that the ring contains a field. That is the assumption. And this assumption has not been removed up to date. So the problem is open. If you want to work on this and not listen to my talk rest of the time, here is a nice problem to work on. If you read the proof of the theorem, it makes use of Griffith-Evans Syzygy theorem, which was true until recently for rings containing field, but now it is true for rings not containing field after all these new developments in perfectoid spaces. But still, this Huneke's result cannot be proved even if you use that. Yeah. All right. Here is coming to 2019. There is another generalization of Nagata's theorem detecting regularity via complete ideals. Yeah. So take a commutative ring as an ideal. X in R is called integral over this ideal if there are elements AI. So that we have this monic equation, and the coefficients are in the correct power of the ideal. The integral closure is the ideal of all elements which are integral, and it is called complete or integrally closed if I equal to I bar. And here is the theorem of Ma, Kwai, and Smirnov, which is available on arXiv. It says let R be an unmixed local ring, and if there is a complete M primary ideal, so that length of R mod I is multiplicity of I, then R is regular. Maximal ideal is complete, and the length is equal to the multiplicity of M, and therefore you can deduce Nagata's theorem. Again, unmixedness is a crucial hypothesis here that cannot be removed here. And so you can take the local ring again, same local ring, kxyz or xy minus xz, and I equal to xn yz, and ei and length of R mod I are equal because it's a parameter ideal. But the theorem is not true. This is not regular local ring. Okay, so take I equal to M in this theorem of Ma, Kwai, and Smirnov, and Nagata's theorem comes out. Okay. Yeah. So now the question arises whether we can characterize singularities in positive characteristic via Hilbert-Samuel polynomial, and that's what I want to discuss. So I will recall tight closure of ideals. I don't think anybody has defined tight closure so far, right? Okay. Yeah. So let me recall this. Let R we have positive characteristic P and Q equal to P to the power E. E is our natural numbers, and take an ideal I generated by A1 up to AR. Then the qth Frobenius power of I is generated by the qth powers of the ideal. This is an ideal because characteristic is P, and Rho denotes the set of all elements which are outside the union of minimal primes. The tight closure is the set of all elements so that there is a C outside all the minimal primes, so that Cxq belongs to the qth Frobenius power for large Q. Okay, this is an ideal, and if I equal to I star, then I is tightly closed, and one can prove that I is contained in I star easily, but I star is contained in the integral closure, and integral closure is contained in radical of I. Okay, so please keep these inclusions in mind. I will make use of these. So as everybody knows, this was introduced in 1986, and it has resulted in many interesting deep results in commutative algebra and algebraic geometry in positive characteristic. And there are many results which were kind of unconnected earlier, but the tight closure theory unifies all of them by producing short proofs and then using the machine of Artin approximation to prove results in for rings containing field, using the same results for rings which have positive characteristic. Yeah, here is the theorem of Hochster-Huneke, which gives a condition which identifies the correct condition for regular rings. Let R be a regular ring of positive characteristic P, then every ideal is tightly closed. Yeah. So when I took the course from Craig, there was no name for tight closure, and they were trying to concoct some name which correctly captures the property. And then one day he said, this is the property, and I want to call it tight closure. Yeah. Yeah. So the closure operation is really tight, that it doesn't do anything to ideals in regular local rings. Yeah. Now the integral closure contains the tight closure, and I want to somehow treat these two closure operations on ideals on equal footing. And so we need to set up some notation which will apply to both the kinds of closure operations, so that certain results can be proved for filtrations of ideals, and they can be applied to tight closure filtration or integral closure filtration or some other closure operations. Okay, so I introduce admissible filtrations of ideals. Yeah. So a sequence of ideals, In, where In is R for n less than equal to 0, is called I filtration. If it's a descending sequence of ideals, and the product of mth ideal and nth ideal is contained in m plus nth ideal, and I require that nth power of I is contained in the nth ideal in this filtration. Okay. All right. So I have the concept of I filtration, and it is called admissible if the n plus kth ideal in the filtration is contained in the nth power of I for all n. Now this condition is actually a condition on the Riesz algebra, which I will state right now. So if F is an I admissible filtration and T is an indeterminate, we construct the following graded algebra. Riesz algebra of the ideal is direct sum of I and Tn. Riesz algebra of the filtration is direct sum of the nth ideal in the filtration times Tn. And we can form the associated graded ring of I. We can also form the associated graded ring of the filtration. Okay, so we have these 4 graded objects, and admissibility implies that all these are finite, they are finite modules. So F is I admissible if and only if the Riesz algebra of the filtration is a finite Ri module. So this is a very strong condition as opposed to what Dale was considering. His filtrations are not even Noetherian. But this says that not just Noetherian, the Riesz algebra is not just Noetherian, it is a finite module over the ordinary Riesz algebra. Okay. And there are many filtrations which satisfy this condition. It's actually a mild condition for large number of filtrations. Because of this theorem of Riesz, a Noetherian local ring is analytically unramified if and only if the normal filtration of I, which is the filtration of the integral closure of nth power of I, is I admissible for some and hence all m primary ideals. Okay. So lots of rings are analytically unramified, and therefore this is a mild condition to impose on filtrations. And I is some any m primary ideal.
So you just take any m primary ideal and this will be true.
Right. Yeah. The Riesz algebra of normal filtration is finite module. Yeah. All right. So since the integral closure of an ideal is contained in the tight closure, the Riesz algebra of the tight closure filtration is contained in the normal filtration. And therefore, if the ring is analytically unramified, the Riesz algebra of tight closure filtration is also a finite module over the ordinary Riesz algebra. Okay. And that allows us to construct a Hilbert polynomial corresponding to the tight closure filtration. So let me first set up the notation for Hilbert polynomial and reductions of filtrations. Take a d-dimensional local ring and I is an m primary ideal, take an I admissible filtration. Then the associated graded ring is a finite module over the ordinary associated graded ring of I, and the dimension of the associated graded ring of the filtration is the dimension of the ring. Okay, these are easy facts to prove, but because of this becomes the associated graded ring of the filtration. The admissible filtration becomes a finitely generated graded module over this graded ring, and therefore one can construct the Hilbert polynomial. So the Hilbert function of this filtration is length of R mod In. It is given by a Hilbert polynomial of this filtration, and we can write it in the usual way in which we write Hilbert-Samuel polynomial of an ideal. Okay. Now I need to know the reduction of a filtration. A reduction of an I admissible filtration is an ideal J contained in the first ideal in the filtration, so that JIN is IN plus 1 for all large n. This is important condition. It should be true for all large n, not just for one n, as is the case in I-adic case. It should be true for all large n. A minimal reduction of F is a reduction of F minimal with respect to containment. Yeah. And we can define reduction number of a filtration. It is minimum n, so that JIM is equal to IM plus 1 for all m bigger than or equal to n. Okay. This is important condition that it should happen for all m bigger than or equal to n. And the reduction number of the filtration is the minimum of reduction number of filtration with respect to all minimal reductions of F. And Ri will denote reduction number of I-adic filtration, and R bar I will denote reduction number of the normal filtration, and R star will denote the reduction number of tight closure filtration. Okay. And so one can ask, what is the comparison between these reduction numbers, how they behave when we take large powers of I, etc. These are unexplored things, except for I-adic case. Yeah. So because the tight closure filtration becomes an admissible filtration in analytically unramified local ring, we can introduce a Hilbert polynomial corresponding to tight closure filtration. So take a d-dimensional analytically unramified local ring of prime characteristic P. I is an M primary ideal. Look at the Hilbert function of the tight closure filtration. This is given by degree D polynomial by general consideration for admissible filtrations. And therefore, there are integers EI star so that we can write the Hilbert polynomial of the tight closure filtration in this fashion. Okay, so just keep star to denote that my filtration is the tight closure filtration. And these coefficients, we will call them as tight Hilbert coefficients, and the polynomial as tight Hilbert polynomial. If you replace the tight closure by integral closure, we get the normal Hilbert function, which has been investigated for last 30 years in many contexts, and the polynomial will be called normal Hilbert polynomial. Yeah. Okay. So the first challenge is to calculate the tight Hilbert polynomial, because it requires computation of tight closure of all powers. So it was not clear to us whether we can ever get our hands on some tight Hilbert polynomial when we started calculating this. And it turns out to be quite a difficult task to calculate the tight Hilbert polynomial. So the first situation we looked at is the hypersurface ring, because there are some tricks for hypersurface rings to calculate the tight closure of ideals. Yeah, so we use those tricks to calculate the tight Hilbert polynomial. And we took the following ring. Take power series ring over a field of positive characteristic and look at the equation xn plus yn plus zn where p doesn't divide n. And in this is a Gorenstein ring of dimension 2, and take the ideal generated by y and z, and this is a system of parameters in this two-dimensional Gorenstein ring. Then we calculated the tight closure of all powers. It happens to be Ik added with the k plus first power of maximal ideal. And we also show that the tight reduction number is 2 less than the degree of the hypersurface. Okay, so you can get any reduction number by increasing the number n for tight closure filtration, even in a Gorenstein two-dimensional local ring. All possible reduction numbers are there. There is no bound on the reduction number. Yeah. Now, if you take n equal to 3, in this case, the reduction number of the tight closure filtration turns out to be 1. And when a filtration has reduction number 1, we have a formula for Hilbert polynomial. And we just use that formula and write the length of R mod in plus star equal to 3 times n plus 2, choose 2, minus n plus 1. So therefore, E2 star is 0 here, and E1 star is 1. Okay, so E1 star is 1 and E2 star is 0. Okay, so there are some coefficients of tight Hilbert polynomial can vanish, and then at that time we ask whether the vanishing of these coefficients can tell something about the singularity. Yeah, and it indeed turns out to be true. Yeah, I want to come back to this computation. How I wanted to show how we can calculate the tight closure of powers of I in hypersurface ring. It involves some tricks with Grobner basis, because in the definition of tight closure, we are asking whether certain elements are in the Frobenius power. Okay, and Grobner basis gives criteria for when some polynomial belongs to an ideal, and we just use that and calculate the tight closure. So I will come back to this if you are interested, and go on to the next slide. Yeah, all right. So hypersurface, several types of hypersurfaces can be tackled, and we can calculate tight Hilbert polynomial. Next we tried this in Stanley-Reisner rings, because Stanley-Reisner rings are easy rings to deal with for many questions. And so take a simplicial complex of dimension d minus 1, and k is a field of positive characteristic, and look at the Stanley-Reisner ring, and M be its unique maximal ideal. Take a linear system parameters. These are the easiest ideal to consider first. So linear system parameters will exist if this field is infinite. Yeah, if it is infinite, and the Hilbert functions and Hilbert polynomials don't change if you enlarge your field. So we can assume that this is a infinite field of positive characteristic. And take a linear system parameters. Then we prove that I star is maximal ideal. this comes out from very easy properties of tight closure, so one of the properties of tight closure says that if you want to test whether some element is in the tight closure of an ideal, go mod every minimal prime and then test it, and you can then come back. So if it is true for mod every minimal prime, then the element is also in the tight closure of the ideal. But when you look at minimal primes of Stanley-Reisner ring, they are very easy. They correspond to facets and they are generated by a subset of variables. If you go mod those, the ring becomes a polynomial ring, and in polynomial ring, every ideal is tightly closed. So because of that, we prove that I star is maximal ideal. Yeah. And this is also true for power product. If G ideals are generated by linear system parameters, then for any S1 up to Sg, the tight closure of this power product is the same power of maximal ideal. Yeah. And so this will allow us to calculate the multigraded Hilbert-Samuel polynomial of these G ideals. And as Dale was talking for non-Noetherian filtration, also we have the set of mixed multiplicities. Those same numbers will occur here for mixed multiplicities of these ideals. But the later coefficients may say something about the singularity, which we have not investigated yet. So take G ideal generated by linear system parameters in R, and take any integers so that the sum is n plus 1. Then the length of R mod the tight closure of this power product of these G ideals is length of R mod mn plus 1 because of this equation. And look at the H vector of the simplicial complex. The H vector appears in the Hilbert series of the Stanley-Reisner ring, and using the H vector and the H polynomial, we can write down the Hilbert-Samuel polynomial of length of R mod Im plus 1 by standard tricks, and that shows that the constant term in the tight Hilbert polynomial of this power product is the last number in the H vector of the simplicial complex. We can also calculate the middle coefficients also. Okay, there's a routine exercise. So in Stanley-Reisner rings, the tight Hilbert polynomial has a very nice expression. All the coefficients have combinatorial interpretation. Yeah. Now let me calculate tight Hilbert polynomial in some other situation. And here I recall a theorem of Huneke about intersections of tight closures of powers of ideals. This is not published. It is in my lecture notes of his course, 86. And it says that if I take a ideal generated by regular sequence, then for all n, In intersection In plus 1 star is In times I star. Okay, this is very useful to calculate Hilbert-Samuel polynomial of the tight closure filtration. So I want to show you that, how it comes. Yes, exactly. Yeah, but that is much more difficult to prove. Yeah, this has a short proof, as it happens in characteristic P. You take a theorem about integral closure and replace integral closure by tight closure, ask whether this theorem is true, and very often a very simple proof comes. Yeah. So I want to illustrate that this has a very, very short proof as compared to the same theorem for integral closure. Yeah. So first of all, by closure operation, I star times j star is contained in the tight closure of I star j star, and this is equal to the tight closure of I times j, and that implies that In times I star is contained in In intersection In plus 1 star. So this intersection theorem is ready-made for this containment. This is equal to In times I star. Okay, and therefore, if I write the generators of this ideal, which is generated by a regular sequence, I pick an element in the left-hand side. I want to show it is in In times I star. So pick such an element. So that element will have an expression because it is in In. In is generated by monomials of degree n in x1 up to xd. So we can write an expression, and A belongs to the tight closure of In plus 1, and therefore by definition of tight closure, there is a C in Ro such that CAQ belongs to qth Frobenius power of In plus 1 for large Q. Okay. So you write down the expressions for these containments. So write a typical expression for A. A is in In, and therefore A is a R linear combination of monomials of degree n in x1 up to xd. Okay. And now use this equation. This says that CAQ belongs to the qth Frobenius power of In plus 1. So raise this equation to qth power and then multiply by c, okay? And then use the fact that this is in the qth Frobenius power of in plus 1. And so I can write this expression where these are monomials in x1q, xdq, and these powers add up to n plus 1. Yeah. Now this is a relation among monomials of degree n in a regular sequence. When you have a relation among monomials of degree n in regular sequence, the coefficients must belong to the ideal generated by the regular sequence. And therefore, if you equate the coefficients of monomials of equal degree, then C yq alpha belongs to the qth Frobenius power for large q, and that shows that this coefficient y alpha is in the tight closure of I, and once y alpha is in tight closure of I, you look at this expression for A, that says that A belongs to in times I star. Okay, so that's a very short proof as compared to the theorem for integral closure. Yeah. All right, so that allows us to calculate the tight Hilbert polynomial for when the tight reduction number is at most 2. So I displayed for you a whole family of ideals where the tight reduction number was n minus 2 in a hypersurface ring. And so if n is at most 4, then we can calculate the tight Hilbert polynomial of certain system of parameters. So let me show you how what this result is. So take a d-dimensional Cohen-Macaulay analytically unidentified local ring of positive characteristic. If I is generated by let I be generated by system of parameters, then if the reduction number, tight reduction number is at most 2, then we have this equation, in plus 1 star is I square star times in minus 1 for all n. And one can translate this equation with a calculation to find the tight Hilbert polynomial of such ideals, and there are only 3 coefficients here. So see that the normal reduction number is at most 2, and only 3 coefficients are there in this tight Hilbert polynomial. And that I feel that the number of non-vanishing coefficients in the tight Hilbert polynomial has something to do with the reduction number. Okay, that is not so clear right now. Yeah. Okay, and this expression is valid for all n, and therefore by substituting values of n, various values of n, I can calculate all the coefficients of the tight Hilbert polynomial, and these are the values which come out. Okay. Yeah. Okay. Now I have how much time? Okay, so I want to now come to the main theme and give a characterization of f-rational rings in terms of the coefficients of tight Hilbert polynomial. So recall that an n-generated ideal of height n is called an ideal of principal class. A ring R is said to be f-rational if all ideals of principal class are tightly closed. So this is a definition of f-rational ring, and there are very interesting properties of f-rational rings. So the ring is of positive characteristic. If R is f-rational, one can prove it is normal. And if it is homomorphic image of Cohen-Macaulay ring, then rationality implies, f-rationality implies it is Cohen-Macaulay. And if R is f-rational, if and only if R is equidimensional and one ideal generated by system parameters is tightly closed. So the definition says all ideals are generated by, all ideals of principal class are tightly closed, but it is enough to show one ideal generated by system parameters being tightly closed, and if the ring is equidimensional, it will be f-rational. So that's how in many examples one proves that the ring is f-rational by looking at one single system parameters and calculate its tight closure and show that it is equal to I. Okay. And it's a local property. R is f-rational if and only if localization at maximal ideal is f-rational. And so localizations of f-rational rings are also f-rational. Although tight closure doesn't localize, but this property localizes. Because for M primary ideals, the tight closure commutes with localization. Yeah. Okay, here are some examples. So ideal, if every ideal is tightly closed, then the ring is called weakly f-regular. If every localization is weakly f-regular, then it is called F regular. A Gorenstein ring which is F rational, if and only if it is F regular. So in Gorenstein rings, if you show one system of parameters is tightly closed, then all ideals will become tightly closed. Okay? These are surprising things in characteristic P, that doing one single calculation, you can then show that all other ideals are tightly closed. Take the following ring, kxyz over x square minus y cube minus z5. K is a field of characteristics at least 3. And take the ideal generated by y and z. This is system parameters. I is tightly closed, and so this is F rational. But this is a Gorenstein ring, and therefore it will be F regular. Okay. So here is an example of a ring which is not regular, but it is F regular. Okay. Since R is Gorenstein, it is F regular. Hoxton and Huneke proved the following result about this example. Take a field of characteristic congruent to 1 mod 3 and look at the following ring, kx y cube y square z yz square z cube over x cube minus yz y plus z. Then they show that this is F rational but not F regular. Okay. And Carrot-Smith wrote this remarkable result. If you have excellent local ring of positive characteristic, if it is F rational, it is pseudo-rational in the sense of Lippmann and Tessier. The pseudo-rationality is defined irrespective of characteristic. It's a generalization of rational singularities when you don't know whether the resolution of singularities exist. Okay. If the resolution of singularities exist, pseudo-rationality is same as rational singularity. So F rational rings, excellent F rational rings are pseudo-rational. Converse is not true. Here is an example of Lippmann. Take this local ring, this is the local ring of the hypersurface x square plus y cube plus z cube. Then it has rational singularity. I think this is his paper in 1969, but it is not F rational. One can depict one system parameters which is not tightly closed in this. Right, but it is not F rational. Yeah. All right, so let me state this result in last few minutes. Vanishing of even star and F rational ring. This is a result of Watanabe. Take a Noetherian ring of positive characteristic. I is generated by regular sequence. If I is tightly closed, then all powers are also tightly closed. Okay, this has a very short proof using Huneke's theorem, which I displayed earlier from 1986. Apply induction on n. Suppose all these ideals are tightly closed. Pick an A in In plus 1 star. Then A belongs to In star because In plus 1 is contained in In. But by induction, this is In, and therefore A belongs to the tight closure of In plus 1 intersection In. But by Huneke's intersection theorem, this is In times I star, but I star is I, and therefore this is In plus 1, and therefore In plus 1 is tightly closed. Okay. In fact, more is true. If you take any ideal which is generated by monomials in the generators of I, it is tightly closed. But this is a special thing, that all powers are tightly closed. If an I is an ideal of generated by regular sequence, and if it is tightly closed. Yeah. All right, here is the proposition. Take a d-dimensional analytically unramified Cohn-Macaulay local ring of positive characteristic, then R is F rational if and only if even star is 0 for some ideal generated by system parameters. Yeah, here is the proof. Take a F rational, since R is, yeah, why did I say this? Yeah, let R be F rational and I be generated by system parameters, then by Watanabe's theorem, all powers are tightly closed, and therefore length of R mod In star is length of R mod In. But I is generated by regular sequence, therefore its Hilbert-Samuel function is simple. It is E0 I times n plus d minus 1 choose d, and therefore the next coefficient is 0. In fact, all other coefficients are 0. Yeah. Okay, so that is one direction. Now conversely, take an ideal generated by system parameters, and suppose even star is 0, then one uses this inequality, which is true for any filtration in a Cohn-Macaulay ring, that E1 star is bounded below by E0 star minus length of R mod I star. This is true for any filtration in a Cohn-Macaulay ring. So I use it for tight closure filtration. And this implies, because even star is 0, this implies that E0 of I, which is equal to length of R mod I because the ring is Cohn-Macaulay, and I is contained in I star, and therefore length of R mod I is less equal to length of R mod I star, but length of R mod I star is less equal to length of R mod I, and therefore I equal to I star, and therefore R is F rational. Here are the references. Thank you.